Good afternoon, everybody. Thanks for coming. Pavilion panel, my name's Jim Hogan. I'm the moderator. I got an august panel here. You know, yeah, you guys. And we're gonna bring up a topic that's getting a lot of discussion around the DAC this year. We're gonna talk a little bit about what we've been working on. These guys don't lack for opinions, so I'm gonna ask them each to do a few slides to sort of set up the discussion. And once we get the discussion going, I'll ask them a bunch of questions. And then I would appreciate if you guys come up with some questions on your own. We'll have a time at, towards the end of the discussion to have some questions and comments. So the abstract, I don't know if you read the abstract. Hey, this is really appropriate, this abstract now here in Austin, right? Because when I did this abstract, I had no idea that Whole Foods was going to get bought by Amazon. But basically, the world's going to Amazon's going to know everything about what you bought online, but it's also going to know everything you bought at the grocery store too. So they're coming to a point where, artificial intelligence is going to be everywhere, ubiquitous, right? There's going to be systems doing everything. So I got a number of questions, right? I'm going to ask Chris to give us an idea. Hey, Chris, where are we? Chris is going to talk about that a bit. James is going to talk about, hey, what's the ecosystem looking like? And then since an EDA show, I'm going to ask, right, how the hell do we verify any of this, right? And so with that said, let's advance the slide. Chris Rowan, gentleman in the middle. Chris is continuing to have a very distinguished career, and you can see that he's been involved in processor architecture and design for a long time. Got a great background. Chris, in particular, has started a new venture firm, and I recommend you go to his website that I give up on top. It's real informative, and I think it'd be a great read if you have any interest in this subject. So at this point, I'll turn over to Chris and operate the, just give him the thing.
Yeah.
Thank you, Chris.
Sure. So when we think about the way the world is changing, I think that we see not just one phenomenon, this neural network thing, but the coincidence of a number of key phenomena which happen to coincide. And it's creating a number of important opportunities and a few challenges. But one of the most compelling, and arguably something that has influenced neural network technology in a profound way, has been the pixel explosion. And I really want to highlight it because I think it is both illustrative of what's going on, but also a key area that is by itself driving an awful lot of new silicon design. And we see this dramatic expansion, this explosion in the number of pixels that we have to process. And there's a couple of different ways of looking at it. One of them is you say, well, how many cameras are there out there? And even if you assume that the average image sensor only lasts for 3 years in the field, in the last couple of years, we've crossed over. We now have far more image sensors out there in the wild than there are human beings to look at any of those pictures that get captured. And what this implies is that virtually all images, virtually all pixels, will be interpreted by machines, not by humans. And all of those cameras will be useless unless we have the means to intelligently filter, analyze, and act on those pixels. And the amount of data is huge. First of all, it probably represents 99% of all new raw data being gathered because the data rates are so large. It completely swamps audio, and audio completely swamps motion sensing in terms of the number of bits. And moreover, the absolute number of bits is well over a petabyte per second, wow, which swamps any network you can come up with, any storage. So you cannot store and you cannot transmit all this information. So it must be consumed, analyzed, reduced, filtered, and acted on locally. So there's going to be an awful lot of vision that's happening. And the fact that it's happening locally means it's vision silicon, and that means design. The second important point is that to do this efficiently, cost effectively, at reasonable power, at the kind of throughput implied by those enormous data rates from the aggregate of all those cameras means that you can and must have new kinds of architectures to do it. And it's really a profound shift in the computing model. For, arguably 70 years or more, we've been developing this Turing von Neumann model of computing, which says, I write a procedure, a human writes a procedure, and the computer follows it exactly. The emergence of machine learning, and especially the important subset deep learning, is in fact a reflection that statistical computing is really important, where you're not trying to get the right answer to a well-defined problem. You're trying to get a pretty good answer, a 99% correct answer to a problem of such complexity that you could never write a Turing machine to do it. It's just humanly impossible to describe all of the things you need to do. And so it's a different kind of computing, and it needs, arguably, a different kind of computer to do it. And there's enormous amount of activity in people building specialized hardware for this. Why? Because in fact, you can do 2 orders of magnitude better in throughput when you're running this kind of an algorithm than if you're running this kind of an algorithm, this kind of a process, on an ordinary CPU. And this chart here shows on a horizontal axis the absolute performance measured in billions of multiply adds per second, which is a pretty good metric for the performance of neural networks. And the vertical axis is energy efficiency. Billions of multiplies per second per watt. And you see this evolution of platforms up and to the right. And it's on a log scale. It's a log scale. And so that progress of points, which is over just a couple of years, represents factor of 100 increase. Now, last I heard, Moore's law was in a little bit of trouble and wasn't providing order of magnitude increases. But this is an architectural revolution that is. So this is a really important shift. And this also is driving a lot of new silicon design and a lot of new silicon innovation. And so the big message to me for neural networks is the use of silicon to create these kinds of systems. I think there's a sub-story, which is also a really interesting one, which is the use of machine learning and deep learning methods to build chips better. And I'm sure we'll talk a bit about both of those.
Sure.
But to me, it's kind of what is fundamentally happening in computing that makes this really interesting. And the last thing I wanted to kind of touch on is just how that enthusiasm is translating into entrepreneurship. I have been trying my damnedest to find out who's doing what. And if you start searching for startups doing some form of AI, you will get an enormous number. I think that number is probably in the neighborhood of about 3,000 startups worldwide who say they're doing some sort of AI. Now, if you look closely at them, some of them are doing a little bit of AI incidentally as part of some other application, or they found some excuse because they're doing a little linear regression somewhere inside of some tool. So they get to call themselves AI because they know that labeling a venture as AI today is a really smart thing to do because everybody loves it right now.
Just like social media was.
Social media was, or internet was, or cloud-based was. You go through
B2B,
your buzzwords.
Yeah. Things like that.
But at the root of it, there are a core of probably 10% of those AI startups that are really seriously committed, doing something engineering-wise that's significant and something that in terms of finding a new application or finding a new method are really significant. And I've sort of identified those 300, and this is a picture of sort of a poster I did that attempts to capture those 300 in 16 different categories. So this is a place, this is eye candy. Go to the website, download the poster, use it to your heart's content as a way to get a handle on it.
It's just like my mom cutting my meat for me. Thank you, Chris. This hurts my brain. This is pretty good.
Yeah. There's also a version of the list which breaks it down by country and by segment and a number of other criteria. So, and it's got all the live web links there. So you can take a poke at it and see something of what's going on. But needless to say, this is a pretty exciting area. And every day, just to take one small category, one of the 16 categories, new silicon startups. And there are about 15 listed here. And since I finished this poster 2 weeks ago, I've identified 3 or 4 more silicon startups in this area. So there is disproportionately rich number of startups here. On the one hand, silicon startups are hard. They've been hard for the last 15 years. They haven't really gotten any easier. On the other hand, this is a domain in which you have both the opportunity to go a heck of a lot faster than a conventional architecture, and the same piece of silicon will do imaging, video, audio, web search. A broad range of applications are all accelerated by this, which is why there actually is enough area under the curve, conceivably, to make a breakthrough in new silicon really becoming viable.
Well, it's probably worth mentioning, if you go back a couple of years, let's say 2014, there wasn't a funded semiconductor startup in the United States. Mm-hmm. So we went from nothing with the advent of, let's say, CNNs to what, how many would you say started this year?
Sort of in the U.S., there's probably 6 or 8 in the U.S. this year.
6 or 8, and these are $100 million kind of investments, right? So that's a pretty significant shift in the investment community. What it means is, I think, is that they smell opportunity, right? Yeah. And they're willing to take the risk where they weren't willing to take the risk only a couple years ago. So this is very significant. Joe mentioned during the keynote that IoT is going to explode designs and stuff. This is an example of that phenomena. We're going to see semiconductor grow quite a bit, not like it grew before, but definitely with new opportunities. Yeah. So as Chris says, his website's really great site for looking at these knowledge. I recommend you guys take a look at it again if you have any interest. Right, mind pass, just forward it and I'll talk about James. All right. Yeah. The handsome gentleman on my far left is James, and James, is a patent attorney, but don't let that fool you. He worked for, let's call it a federal agency that looked at spatial things from 100 miles away and tried to determine if there was some, let's say, targets of interest. And so in that, you have to process a lot of pixel data and put some intelligence around that. What he doesn't list on here, I don't think, is, there it is, the Qualcomm. He was the patent counsel for Qualcomm, took care of the software stack for things like Snapdragon. And he's been admitted to the California bar and probably omitted the fact that he was admitted to the hospital for some kind of rehab or something. But anyway, James is going to hopefully enlighten you a little bit about where we are in the ecosystem right now. Go for it, James. Those colors work really bad. Sorry about that.
So let me just talk a little bit about some of the challenges to take advantage of the changes that Chris referred to. If you want to embrace machine learning for a vertical application, there's a daunting array of technologies that you have to become familiar with to take advantage of the different platforms. Now, some of that is getting better, but I think that there still will continue to be a lot of challenges and opportunities around the tools and the ecosystems. What this slide is really intended to convey, although the colors are a little challenging, is a summary, a snapshot of some of the technologies that are available in the cloud. The early technology that gets a lot of discussion and use and is used pretty widely in the cloud is Caffe, that came from Berkeley Vision Labs. And this is a technology that's widely used to define network topologies and perform training of networks. And it continues to be very important in developing training models for that can be accelerated and perfected in a reasonable amount of time. And that historically was a challenge with machine learning, is that we were unable to train deep neural networks in a reasonable amount of time. And what has happened that's really enabled this revolution is, first was the use of the GPU to perform gradient descent and training of convolutional neural networks, and to be able to do that in a reasonable amount of time. And Caffe was kind of one of these foundational technologies that came out of Berkeley Vision Lab that enabled people to actually begin experimenting with deep neural networks and training them and applying them to problems. You know, there's been a lot that's happened since some of these early tools have come along. Everybody is now, and you know, has a scheme, I think, for a new tool, software tool. Google, most notably with TensorFlow, has gained a lot of traction. Caffe 2, which has been being promulgated by Facebook, has become a significantly interesting technology for both training and deployment on the edge. And you know, if you want to solve the pixel explosion problem that Chris referred to, as an organization, you have to learn these tools and this ecosystem, and you have to have people who can leverage these tools to rapidly create and apply models. And so, you know, coming from a background, you can think about some of the earlier technologies that some of these emerging technologies are layered on, things like OpenCL and programming standards for GPUs. There's a new wave of standardization that will probably have to occur to kind of consolidate the ecosystems that are a little bit fragmented at this point. So you know, a challenge and an interesting thing for discussion, if you're trying to make sense of all of this, is how do we use this? If I want to create a deep learning application, I have to master this array of technologies in the cloud, and there's a whole nother array of technologies for the edge. And again, the next slide really kind of talks about who's doing what at the edge. Once you have a model trained in the cloud, you have to, if you want to use it on an edge device, you need to execute that model, perform forward propagation efficiently at the edge. There's a lot of different schemes for doing that, and there are many different devices that can accelerate that, from a CPU to a GPU to a DSP. And how you take advantage of those different devices at the edge. There may be fixed function hardware that emerges at the edge that gets incorporated into some of these SoCs from Qualcomm and others. And so how you take advantage of that in a platform independent way is if you're trying to develop an application stack, that can be quite a challenging question. Again, you know, standards are important here. Many of the solutions at the edge now for acceleration of these models rely on OpenCL, which is something that is a programming model, with the exception of NVIDIA, which is based on CUDA. So you know, many of the solutions currently at the edge are layered on top of OpenCL. I think an interesting question for discussion is, you know, what's the opportunity space around the tool chains here? You know, who
is there an EDA of AI or something like that? The tool chain and the stack, an IP. Yep. So there's an analogy, right? That might work.
Yeah. We'll come back around to it.
Yeah.
I think there is. I mean,
Yeah,
I think there's
I agree.
some close analogies between some of the things that have made for good tools for EDA.
And good IP.
And good IP, for sure.
Yeah.
And what is potentially available.
Yeah. James, you good?
Good.
Okay, you mind handing the clicker over to Wright? So first of all, everybody look, turn your heads and look at Reich's water tower up there behind you. You know, Reich's the CEO of OneSpin. You know, he's had a lot of time to develop the methodology for dealing with verification, in particular verification that's coming of age, I believe, and for very complex systems where you can't imagine every function you have to test. So you got to have a system that does that for you, and for completeness, thoroughness, and terms of absolute ensuring things like safety, for example, right? So with all that said, I thought it'd be really interesting, because he has a personal interest in AI, all right, what's going to happen when you get these AI processors going, and how the heck are you ever going to verify something that changes its own function, right? So that hurts my brain even thinking about that. So Wright, it's all yours.
Thanks. So before we dig into that question, I would like to illuminate a little bit on the history of how AI and especially formal verification are connected, because you can see quite some resemblance of the way things have been happening. Back in the early days, it was actually considered the same thing. Artificial intelligence and automated reasoning and deduction were the first type of AI back in the 50s and 60s.
Sure.
That came to a really stop when people found out that the early models for learning weren't actually performing well enough and had some fundamental limitations. And I believe that at that time, lots of the guys who invested their careers into logic and deduction, they said, oh, what are we doing with all these things we have developed here? The AI thing is dead, so let's go for verification. Let's invent formal verification and do something with it. And out of that came a whole chain of innovations that were around how do you do automatic deduction for hardware verification and logic. And interestingly, one of the most important algorithms that we use is based on Davis-Putnam and so long learning algorithms for Boolean satisfiability. So we do actually do a fair amount of learning on the fly when we verify formally that some function is what you're expecting. It's not statistical though. So it's a fundamentally really complete and mathematically thorough approach. So how does that connect with verification of statistical models and all these things? Now, that's something we will talk about. What happened in AI and specifically for deep learning is that with the availability of these platforms and especially the DSPs and graphic accelerators that were used for this, you could actually perform these things. So silicon had one important role in that, making it happen. Because before that, it was just not possible to do things. And nowadays, we're thinking about how we can apply all this technology again back in our space. So there's a lot of work going on in the EDA industry on how we can leverage machine learning technologies, deep learning, into making our products better. That's something I think everyone here you will think about, and what they will say to you is that they have someone there, they're doing machine learning, they're analyzing their data, they're trying to analyze the customer data in order to make smarter decisions about the flows and the things they provide. And so do we. So fundamentally, everything is connected in some way in artificial intelligence, and in some way, people say when it works, it's no longer artificial intelligence. So that's the thing. So what we do, we don't consider AI anymore, even though it's based on the foundations of AI that go back to the 40s and 50s. And I'm not sure when we will reach the point when we see another dip in AI, when we see that the general AI thing doesn't work out for us, and the deep learning is just one very good thing to make things work. And it becomes an engineering thing, it becomes an engineering class. It will no longer be AI, but it will be deep learning, and it will be a very important part of our life. I think that's what we all agree on. So the question is, what does it take to get there? So the key things that we have seen is, that's one of the most important things to have is a platform that you can build on. And that's what the whole software stack is providing today. You want to have an abstract programming model that you can use in order to derive your conclusions, and you put your implementation in place. And of course, you need to have a hardware that you can map that to. And I think that's where the challenges come, because the power that you actually require to perform all these functions is enormous. And that's coming from a fundamental architectural problem in the von Neumann architecture, that you have storage and memory separated from the compute. And the amount of data transfer you're doing between these compute nodes and the memory is for these deep networks, especially on the convolutional networks and having these pixel explosion problems, is just enormous. It's terabytes per second that you have to feed from the memory to the processing node and back. And there are several approaches how to address that. One is the GPU, and the other is the DSP. I'm borrowing some information that I got from Qualcomm here on their Snapdragon devices. So basically, if you trade in some of your flexibility that you have as a CPU platform for your architecture, you can get a better throughput and a better power consumption. However, when you look into the requirements of special edge devices that we will talk about, that are maybe variables or other things, you're going into a range that is just not accessible to this technology. So there must be fundamentally something that we need to do differently about how we compute. And what people believe is that moving data and computation together is the way to go. So that can be distributing DSPs and compute around the memory. It can also mean fundamentally different computing techniques that are more close to like feed-forward computation that we have learned in school maybe, and that never took off. So in the end, I think moving the compute to the data is the big thing on the architectural side. What drives this on the edge is the requirement for latency. So you have to make the decisions very quickly, and you cannot rely on the network and the back end in the cloud to compute your answers. So the feed-forward computation is required to be very low latency. Privacy is another concern people have on the edge. They don't necessarily feel comfortable with loading up all the data they have into the cloud. And reliability is another concern. Because the service you're providing at the edge needs to be reliable in several conditions that may not have a network connection, or several conditions in an environment that you don't control. And last but not least, one thing that comes up now is context awareness of the devices that you put in place. So what if you had a device that would actually be personal to you, some variable that is able to recognize the people you are dealing with, rather than generally having someone telling you there's a person in the picture. You don't need that in your glasses. It's maybe something you use on the show floor that identifies the people you have met before and says, oh, this is Jim Hogan. Maybe I should say hello to him, even I don't remember the guy.
Or well, you maybe should avoid him.
Yeah, that could be too.
Yeah.
You just take the other aisle.
Yes, yeah.
But that's something that is the context awareness that you can put into devices if you embed the learning into the edge. And that's going to become the next challenge in this whole thing. I believe we can scale on the compute side and the compute farms and in the cloud quite for some time. The technologies are just, it's not easy, but they are scaling up. It's having GPUs bigger and better. It's having more DSPs and low power. These things we can address with more or less with the same technologies in EDA, for example, that we have available. There will be some things that we will need. There are challenges like clock distribution that will be very difficult to solve and things like that, but it's not a fundamentally different thing, right? At the edge, though, we need to look for devices that have a very, very low power, very high performance. The cost is an enormous factor, and reconfigurability and security need to be in there. So this is an enormous challenge. And I think that will drive new hardware platforms that we will see in the next couple of years. The only question is what they will look like. And that's the thing we haven't figured out yet. There are so many different ideas around how to perform learning at the edge, for example, is a big challenge because of a fundamental problem of how deep learning works today. you have to compute the transpose of your feed-forward matrix and feed back the information in a symmetric way. And that actually kills your performance and your power consumption, so that's not a good idea. So people look into neuromorphic computing. The brain doesn't work that way. So how does it do that? And inspired by these things, people come up with new algorithms how to perform the training now. There's incremental learning that people will apply, adding to the network that you actually deployed. And all that comes with the verification question. So what is the verification going to look like? There's several things here that we need to consider. One is the verification of the platform itself. I think that's a space that we hopefully can make a contribution to and understand what customers need and just develop what we have today. But there's one fundamental difference in the whole scheme of how this ecosystem and the application of AI works. It is the retraining of your network and the statistical nature of the thing. These two aspects are actually making it different. The statistical part is you can no longer prove anything about the system you're supposed to deploy. You can only give a statistical reason that it works in most cases. So you will see maybe things like in automotive safety that you give a statistical guarantee that the network will perform in a certain way and have a certain error rate. This is a type of verification that you might address with different technologies. The more interesting thing for us in EDA is the retraining of the network. So if you have a system, if it's a car that you own and it's getting new data from the data center pushed into your device and feeding back some data to the cloud and retraining there, you have to reperform the whole verification cycle again and again. Not for the platform, because that's something that you have built and you have verified, but the training that you do in the network changes maybe the architecture if you do incremental updates to it. The way changes might not be so important, but if you want to guarantee a certain performance, you have to redo the verification all the time. So previously we have been doing design, verification, deployment, and then decommission the device or the thing. Now we're doing design, verification, deployment, all over again. And maybe there's an opportunity for EDA in this space to provide tools that are used in this flow to do this verification. I think that's maybe an interesting thing to do. If we can sell to anyone doing deep learning, that would be fantastic for us, wouldn't it?
Can you forward a slide, please? Well, thanks, Wright. Thanks, Chris. Thanks, James. This is another one of Chris's slides, actually taking the same data he talked about in the Cognitive 300 and looking at it a little differently, right? I happen to like this slide because it really helps inform the discussion. As you can see that the majority of the opportunities that he's looked up using Crunchbase is that they're around visioning, right? Visioning is an edge-based solution, a lot of pixels in it. And so you look at a lot of the things we're going to talk about, I think you got to think about edge and how much data is presented on the edge in terms of image data. And so I think that's a place we'll see a lot of intelligence emerge, right? The other couple things before we begin the discussion, what I think it was said a couple times, you know, AI's been around a long time, so why is it important now? It's important now because, one, there's tons of data, pixel data, right? So that's number one. The advent of AWS, Amazon Cloud Services, and the ability to access a lot of compute power as well as a lot of information itself. With those two things, you can apply the deep learning algorithms to actually learn some things. So it's emerging now because it's finally, the time has happened. We're going to be inundated with these things. It's going to create a innovation wave that's going to go on as long as I'm around, I think, and probably change mankind pretty significantly. So with that, let me start peppering the panelists with some insightful commentary here. And so, you know, it all sounds great, right? Yeah, let's go for it. Right? You know, so, you know, let's start with what's your biggest concern, you know, with the advent of these things, right? I mean, It can be a technology concern. It can be a social concern. But I'd love to hear what you guys think, right? James has always got an opinion. You know, he's a lawyer, so he's franchised ethics. So I'll go to James first. What's your biggest concern?
Oh, well, I mean, I think privacy and security always has to kind of bubble to the top of that list. It's just a matter of when this technology is going to be commonplace in the devices that we all carry around. And I think that the security and privacy implications of how this technology could be used probably aren't that well understood right now.
You know, so I was on a panel discussion for Cade's 2 panel discussions, and every time you do a panel discussion, they give you a nice party gift, right? So I got 2 Echo devices, and I said, great, now I got 2 ways for the board to listen to me, right, and know where I am. So yeah, I'm a little bit concerned with security and personal privacy. Chris, what's your concerns?
I'm thinking about how we translate this enthusiasm into real products, because we have this groundswell of enthusiasm, but the number of really knowledgeable people is so small, and you have this, this cone of pyramid of knowledge where we need to move a lot of people from being enthusiastic, who have, taken the Coursera course from Andrew Ng on machine learning.
Stanford. Right.
Yeah, and start to get them into really sophisticated practitioners.
Who's taking the course? Yep.
Yeah,
There
it's
you go.
okay.
The first day that
I
course
still hired someone.
the
who
first
does
day
that.
that course was offered, it broke the internet.
Yeah.
Yeah, there was like 100,000 people signed up, and then Andrew says, "How the hell am I going to grade all those papers?" So they shut it down for 6 months till they automated the course so they could do the certification.
Yeah, it's
So
the
anyway,
origins of Coursera.
origin of Coursera. There
Yeah,
you go. Deep learning on Coursera.
And so we have to figure out how to propagate sophisticated knowledge about the techniques, and even more importantly, about how to think about the end applications. I mean, everybody understands, image classification and localization and object identification, and everyone understands, at least in principle, automatic speech recognition. But what's the best way to apply it in a CAD problem? Or what's the best way to apply it to an information kiosk or to a garage door opener? And there will be hundreds of thousands of products that get created over the next 10 years that really use it in an interesting way. And we have to figure out what is it a good answer for and what's not. So there's a really big challenge of educating and bootstrapping a whole community of engineers and getting them to think about all the dimensions of it. Where do they get the data? How do they train it? What is actually the product experience? How do they protect privacy? How do they avoid creating new kinds of security holes in the system? And they have to really embrace that. And it is enough different from what people are used to in traditional hardware and traditional software that there's kind of some mind-bending dimensions to it. And that, to me, is number one.
Yeah, so to put some more meat on the bones, if you look at, so I'm probably the oldest man in the room right now, so when I went to undergraduate school, I got a math degree and general engineering degree because there wasn't a computer science program at my college. They didn't award computer science degrees at San Jose State when I went there. Now it's the biggest school in the whole college, right? I mean, they graduate 4,000 guys in computer science a year. And so the point of the story is every university with an engineering program or science program has got a computer science degree. So, all right, that was 40-something years ago. But where we are, we're on the verge of this new science. It's called cognitive science. To give you an idea, one of the early Facebook guys, engineer named Tanner, got a bachelor's degree, computer science from UC San Diego. And he donated $65 million to create the School of Cognitive Science at San Diego's University of California, San Diego. So I bet within 10 years, we're going to be minting cognitive sciences, both at research universities as well as universities like San Jose State that populate the companies that we all work at, and it's going to be commonplace. One more comment. I read too, some of my research data said that we're looking at 25 million apps in year 2020. Now that's a lot of apps, right? So some of these things are going to be apps that are going to be driven, a lot of them are going to be driven by AI. 25 million, right? To give you an idea, on a smartphone, Google buys an app company every day between $20 and $40 million. So we're talking about an industry that is going to be, 5 times bigger than this hall within 10 years. So, right, what's your biggest concerns?
Yeah, I share the question about privacy, but what concerns me most is the reliability and trust in the system that you're building. So until now you had engineers building systems and they were able to explain what they did and how they did it and why it works, and that is all not true for statistical models. So these cognitive sciences have to come up with some way of explaining themselves. The AI has to come up with some way of explaining itself. You got to ask it, why do you believe that is a good decision? Why do you believe this is what you want? And it becomes even more relevant when you trust the system for important decisions about your life. Put the brake pedal or not, avoid some obstacle or not.
How about get married or not?
Yeah, that's another one. You can, there are countless possibilities where things can go wrong, and if trust is built by exactly explaining why it works, and that's a fundamental thing that's missing nowadays. So there's still a gap in this whole thing.
Yeah.
One trust question that we may be able to address is the flow. The whole ecosystem is a large stack of technologies that you put together in order to provide for a new version of your feed-forward reasoning in your edge device or whatever it is, or your car. Now, who is making sure that there's no bad guy in the middle doing something to your data, right? You have to think about how you can actually qualify this whole chain of tools that you're using so that you can trust that what you put in the beginning is what you get in the end. And believe it or not, if you think about it, if you have these devices deployed all over the place, that is an enormous power. If you can make changes to these things in ways that you don't foresee or don't like, that's even worse than the privacy question. So I think that's one of the big challenges we'll have to solve.
Yeah, so let me try to give you an example that happens in my life here in Austin, right? Siri, who's got an Apple smartphone? Folks, have you ever asked Siri, tell me what the best restaurant is in Austin, right? And it tells you the county line for barbecue, and it's a 4.1 star or something. Okay, well, is county line paying Siri? Did you influence that decision? Why is there credibility in that? And I mean, today we're pretty accepting of that, and when we do that, it's exactly what he's talking about. What was the criteria that made that decision, and is that a valid criteria? Should we trust the result, right? And so I think that's going to be a huge question. One more story, then I'll stop, and then we got to get the last comments from everybody, because believe it or not, we're going to run out of time. So last year I bought a new truck. I bought a Ford. I live out in the country, and there's a Ford agency about 40 miles from me, so I went online late at night like old guys do and said, hey, what's the inventory? And I'm looking at the inventory, and there's this little box that comes up the side and says, hey, can I help you? There's a nice young lady sitting there going, my name's Jenny, can I help you? And I go, sure. I had some questions. So I'm interacting with the box for about 15 minutes. Then it finally dawns on me, hey, I should ask this thing if it's a robot. And so I was into it for 15 minutes before when I asked it was a robot, it transferred me to the person on the phone immediately. So I was talking to a bot for 15 minutes before I even knew it was a bot, and I'm a luminary. I got to laugh because we're going to experience this stuff and not even know it, right?
That's Turing test all over it.
Yeah, there you go, man. So anyway, this will be the first of a lot of these conversations, right? And I'm looking forward to the next couple of years because I think the darn thing's just going to go like heck. We don't have time to get to the opportunities to talk about the analogies with EDA today too much. I apologize to you guys, but we just ran out of time. First, I'd like to thank my panel. Would you guys please give them a hand? And I'd like to thank the DAC organization for once again allowing me to have a presentation without really asking what I'm doing again. And that's been very useful. So thanks a lot for attending. Come on up and talk if you like. Thanks so much.
Hey, thanks a lot.
Oh, yeah.